Thank you. Thank you. Just to, so everyone knows what I'm talking about, what I mean by real time in this situation is that we created an animation while the tsunami was still crossing the Pacific Ocean and made it available. And the tsunami in question is the April 1st tsunami in Chile from the 8.2 magnitude earthquake there on April 1st. The next slide. So just to give you a little background, how this all worked was we have a real-time forecast model we've been using for a few years now that we developed in-house called RIFT, and the R stands for real-time. And this is built for speed. It uses linear equations and parallelized code, so it can crank out a Pacific-wide tsunami forecast in about 15 minutes. And it uses centroid moment tensors as sources. More recently, we've started to use W-phase seismic processing in order to get us also a centroid moment tensor in real time, or near real time, I should say. We can get that in about 25 minutes after the earthquake occurs, and that's due to waiting for enough data to arrive from the sensors deployed in the field, and it also gives us another moment magnitude. And my particular contribution is I've written the animation code, and I've also built this for speed. I say multi-threaded and put that in quotation marks because the way this works is we chop up the script, if you will, or the sequence of the animation in parts. And if you have 8 processors, you have 8 parts and they all run simultaneously. So you can speed it up that way. And the other thing is I'm using the computer's memory as if it were a hard drive. And this speeds it up considerably because the software I'm using to generate the images is generic mapping tools. Its first output is PostScript, and you have to convert that into a bitmap image, and then that becomes one of the still images in the animation. It also helps because each frame of the animation represents a net CDF grid that has to be parsed and turned into that PostScript. So next slide. And for more on why this worked, at PTWC we've had a major computer refresh a couple of years ago that got us servers that each has 12 processing cores on it and 48 gigabytes of RAM. So there's the multi-threaded I described and a lot of RAM that we can run our software in. The earthquake, as I mentioned, was on April 1st. In March I was working with a lot of outreach activities that were in preparation for the 50th anniversary of the Great Alaska Earthquake and its tsunami. We had some events for that. April is also Tsunami Awareness Month in the state of Hawaii. We have a month-long things that we do for outreach activities, and I was creating content for that. And also, we were preparing for the ASEAN conference. That's the Association of Southeast Asian Nations. This was, and they were meeting in what would be our new building for PTWC. And so I was creating some content for that as well. So because of us already sort of spinning up for this kind of work, we were already prepared to make animations because I was already doing it. And then last year, PTWC got its own YouTube channel. I've been creating content for that and refreshing it. And in our new building, we also have a Science on a Sphere exhibit from NOAA, which was used as part of this ASEAN conference. And I'll show you an example of that in a minute. So next slide. So this is just what we know about the earthquake after the event. This is sort of the official parameters. This is the NEIC parameter, so it was a magnitude 8.2. It was shallow, 25 kilometers. You see the global centroid moment tensor there. So it shows that it's a shallow thrust, basically the worst kind to make a tsunami. And it did, in fact, make a dangerous tsunami in the near field. In Chile, at one point recorded over 3 meters in height. But in the distant field, far field in Hawaii, it was only about 20 centimeters, a little bit more than that. In Japan, there was an observation as high as 60 centimeters. But the earthquake's what caused most of the deaths there. It was 6 deaths in Chile and 9 injured in Peru, I believe it was. And then, as you see, 2,500 homes that were damaged from the earthquake. Next slide. So I'm going to step you through a timeline of how this progressed in the Warning Center, and each frame will be a still frame from the final animation. So this is at the 1 minute mark. This is when we first knew there was an earthquake. Our alarms are sounding in PTWC. And if you look in the far left of the frame, you'll see a tiny little tsunami starting to form there on the coast of Chile. So next frame. So 8 minutes afterwards, we were able to get our first warnings up. This is using our old protocol. We have a newer protocol as of October, but within 3 hours travel time of the tsunami, we put up those nations into a warning status, which was Chile, Peru, and Ecuador. Watches for 3 to 6 hours out, so Colombia, Panama, Costa Rica. Our first magnitude measurement was an 8.0. If you recall, NEIC now calls it an 8.2. And we had it somewhat shallower, but the location's about the same. So the next slide. And then we got our W-phase solution. That's the moment tensor in a revised magnitude. So now it's about an 8.2, but it tells us that it is, in fact, a shallow thrust earthquake there. And you can see the tsunami starting to progress across the ocean there. So that's where it is at about 32 minutes after origin time. Next slide. And then, like I said, it takes about 15 minutes to do a Pacific-wide forecast using the rift model. So then we have the rift solution at this point. So now we're about 45 minutes after the earthquake occurs. So we have our first rift forecast in that next slide. And this was what the analyst in the warning center sees on the screen is an image like this for the rift forecast. So this one is showing you what we call the energy map. That's deflection from normal sea level caused by the tsunami on the open ocean, not at the coastline. But you can see that it's pretty confined, pretty narrow beam, right, and it's focused right close to the South America margin. The next slide. And then this is what our estimate of Runup would be for this event. This is just using a simple Green's law approximation. But you can see right on the South America coastline, there's white and magenta dots. Those are what it predicts would be the worst case. Whereas in the far field, it's all sort of the cooler colors that are much lower. And if you can see on the scale bar at the very end, it says this is a little over 4 meters. Like I said, it was about 3 meters was the worst one that was recorded. So that's not too bad. This is a model that's good enough for telling you where the tsunami is going to be dangerous. So that's what we use it for. The next slide. So about 5 hours after the event, we had enough between the model and measuring the tsunami on coastal gauges and dart buoys and so forth. We were satisfied that the threat had passed for South America, and we dropped our warning for South America. But at the same time, we raised what we call an advisory for the state of Hawaii. An advisory is a type of message that basically says you don't have to evacuate, it's not that severe, but stay out of the water because of those dangerous currents like we saw earlier this morning. And stay off the beach, stay out of the water, but you don't have to evacuate. So that's that type of a message. And at this time, we felt it was okay to make a public release of our first animation. I had been sort of cranking on it at the same time and gave it to the news media locally, showed it on their computer screens, gave them a digital file, and after it was broadcast, I noticed there was an error in it, just the time was wrong. So I had to start making a new one. So that's the next slide. So it took me a little while to troubleshoot the code and get it to work, but 7 hours out, I had one I was satisfied that was good for public release on the website. So I start working on that at 7 hours of when the code starts running. You can see how far the tsunami's traveled there. Next slide. And about a little over half an hour later, the animation is done. Next slide. And then it takes another 45 minutes roughly for it to appear on YouTube. And that 45 minutes is a combination of upload time. This is a bandwidth issue. Uploads are always slower than downloads. But also YouTube itself has to post-process the video and prepare it for streaming. So that takes a bit of time too. So all in all about, so a little over an hour and a half, something like that, you can have it up on YouTube. So next slide. And so this is the animation itself. This is what's still up on YouTube. Anybody can see it. And so what I like about these is you can see how fast the tsunami is moving. It gives you amplitude information. You can see there's a color scale on the far left. These are all bluish waves, which tells you these are all tiny waves on the open ocean, that they're not big dangerous waves. You can see that, get an idea of the frequency of the waves and so forth. And basically this provides anyone who looks at a whole lot of information rapidly. There's gigabytes of data here that you can ingest in a few minutes just by watching the animation. And it shows you where it's going to go, as I said. And so it takes about, I think the animation runs for a simulation of 30 hours. It reaches Japan around 22 hours. And that's another reason that we were able to get this out in real time. This tsunami is in the Pacific. It takes a long time to get all the way across. And then at the end here, it starts to fade in an energy map that I showed you about that shows the maximum run-ups are confined mostly toward the South American coast. And it stays on that image for a little bit to let people sort of digest that. And then here at the very end, it's going to transition into the Green's law run-ups that I mentioned a second ago. And let's see, any minute now. There we go. So again, you can see the worst cases right on the Chile-Peru border, and everywhere else not so bad. There's a few warm dots like you see up in Hawaii, which we put in the advisory status, as I mentioned. And next slide. So there's where so we canceled the advisory for Hawaii about over 12 hours after it started, but above, just shy of 4 hours after the first waves arrived in Hawaii. So about for 3 hours and 40 minutes, we were watching the waves, making sure there was nothing too dangerous in Hawaii, and then we were able to cancel it. So that's now at 7:25 in the morning in Hawaii the next day. Next slide. But there's still more to come, which is, I mentioned that ASEAN conference. That was being held on April 2nd. That is the same morning. So the next slide. So here's Dr. Sullivan, the administrator of NOAA, was in our building giving his presentation. That's Chuck Hagel, the Secretary of Defense, and his counterparts from a number of Southeast Asian nations were all there, and she was able to use our animation on the Science on the Sphere, which is a spherical projection system you see in the upper right corner, and gave that presentation that morning to these people. Next slide. And that's where the tsunami was while she was talking. So she was giving the presentation while the tsunami is still crossing the ocean. So this is I find to be I'm proud of that, I'll say that. Next slide. So reactions outside of PTWC, as I mentioned, we gave this to the news media. Local media picked it up. They passed it up the chain to the national broadcasters. I saw it on CNN and NBC. It also showed up on some web-based news magazines like Smithsonian. Also, emergency managers were looking at our YouTube channel. One of our colleagues at the Weather Service headquarters was coordinating with FEMA, and he was going to give them a copy of this, and it turns out they were already looking at it. So they were already on the same page and could move forward from that. And then as of last week, we had about 660,000 views on YouTube. I know it's tiny compared to Funny Cats, but for a science video, that's not too bad. And that does not include anything that was broadcast. I'm sure it's in the millions of people who actually saw this thing that I can't count using the YouTube counter. Next page. This is just some search engine bait that I happen to find. The tsunami explodes across the Pacific apparently, and it takes over the entire Pacific, and my favorite, it bends mines as well. Next slide. But because of all our experience with this, I have a lot to think about for the future. One thing is, I mentioned I had some errors in this. That's because I was adapting code on the fly while this is going on. That's not the way to do it. A better way to do this is have this automated. The two warning centers are getting a new software system next year, hopefully, and I've been working with them on trying to get some animation component in that, so it should be a push button solution for whoever is on duty at that time to be able to create one of these things on the fly as necessary. But hand in hand with that, we need to develop some protocols and policy about what's the best way to handle this new data set. When do we release this to public or to emergency managers? When do we do it? Who do we release it to? Those kinds of questions need to be answered. But also, and I say education and outreach, that's of the people, we're basically training people how to read these things when we give them to them. You saw from those sort of lurid headlines, they're somewhat misleading. This was not a big tsunami on the open ocean away from the earthquake. It was a sensational media coverage, but it's somewhat misleading. If we start generating these things routinely, there needs to be some training of both emergency managers, our colleagues and so forth, but also the public. And the analogy I like to make is that anyone can go to a Weather Service webpage and see radar animations. They can see satellite photo animations. This could be another tool, but like there needs to be some standardization. The next slide, please. And that's what this is an attempt here. This is another animation I created. This is a still frame from it. This is 3 tsunamis, all from the same region. They're all from Chile. At the same point in time in their sequence. So this is 4 hours after origin for all 3 tsunamis. The one on the far right is the one from this year that got all that media attention. And I'm using the same color scheme in all 3 of them to make the point. If you look at the other 2, there's 2010 there in the middle, which was definitely a dangerous tsunami and had some risk in the far field, but not nearly as bad as back in 1960. And there you can see them side by side. If we have folks to understand that green and red colors that's bad, way, way worse case than it is on the far right. That's the one exploding across the Pacific. That's the one that's taking over the ocean. So thank you. If there's any questions, I'll be happy to take them. Yeah, Mike.
I should probably know the answer to this, but so you're waiting for the CMC result before you initiate the model, I think.
Right. That's correct. Yeah, the model can use any CMT. We can use a historic one from a database, but if you want to be as accurate as possible, you want to.
I guess that's my question: is internally, are you looking at historical sources or maybe even sea-level sources? If we have like the 4th generation DART, maybe to do an initial assessment, or how do you see that?
Well,
can you repeat the question, please?
Okay. He was asking about what the sources we use for the model, and if we're using sea level data as well. In terms of the time frame here, 45 minutes after the earthquake, we don't have much sea level data yet. And so
if you have like a 4G DART, theoretically you could put right on the source and get.
I'm not as familiar with that technology, but yeah, if there is a way to get pressure data from close to the source, certainly we'd want to use that to characterize the earthquake. The rift model, though, is geared towards deformation of the seafloor, and if there's any way to get that information, then that'll help.
You need that, though.
Yeah.
That seafloor depth.
Right, right. Eddie?
Great presentation. I noticed that you showed the data from this Chilean tsunami, and it was 60 centimeters deep. Is that correct?
Right, that's an observation. That's not a published result. That's something I found on a news article, and somebody stood on the coast, on a coastline somewhere.
You showed your, the green dots all around the Pacific. I didn't see anything red.
Right. The Green's law is, as I say, it's an approximation, and it does not capture the details in the coastlines and so forth. I don't know the details of where that 60 centimeter observation was. I don't read Japanese, so I need to get someone to translate it for me. But the Green's law basically takes on, well, you know what a Green's law is. I don't need to. Right. Well, yeah, go ahead and back. Well, if you look at the map, it doesn't have all of Japan on it either. So I don't. That dot may have been on the north. I don't know where that was. You have to go back quite a ways.
We need to move on.
Oh, okay. Go to move on. Sorry, I can show it to you later.
Thank you very much.